Then hello everyone to our first seminar on interval methods in control engineering in the year 2023. It's my really great pleasure to welcome all of you to the restart of our seminar series. And especially I wish that all of you has already had a nice start into the new year, and hopefully all of you will stay healthy. I wish all of you a very successful new year. And yeah, without further ado, I'll now hand over the microphone to Fabrice. Fabrice is working at the ENSTA Bretagne in Brest, and he's a long-term researcher in the area of interval arithmetic with applications in various types of robotics, especially also underwater robots. And yeah, Fabrice, the floor will be yours to present your work on preliminary design on an interval-based autopilot.
Okay, thank you for your introduction. So first I will try to talk about the problem that we have, and I will start with a little bit of vocabulary about the vocabulary I will use. So what is an autopilot? So an autopilot is typically a device that we find in typically aerial drones, but not only aerial robots, which is combining several sensors, typically inertial magnetic sensors, and also a lot of inputs and outputs to connect other types of sensors, such as GPS, communication devices, and potentially other sensors that can be used for state estimation. The big addition to this is inside the autopilot, you have also a processor with control algorithms. And the idea is inside this autopilot, you have a lot of state estimation algorithms that are supposed to give the best estimate for each important variable of the robot, as well as control algorithms that needs usually to be defined or tweaked by a lot of parameters, so that the autopilot knows which type of robot and actuators it needs to control. So most of the time you have some pre-configured profiles or robot types, and some typical navigation algorithms that are already that we are already able to use using the autopilot quite easily. So this is an example of a typical autopilot. So this one is a Pixoc. It's quite open source, open hardware autopilot. So this one is one of the first version. Now they are at something like the 5th or 6th version. And this type of autopilot is typically used in aerial robots, so for especially for DIY robots, but not only. It can have algorithms for surface vehicle, ground robots, and also in typically the blue ROV submarine robot. Then we have what we call the inertial measurement units. So I would say, to me, an IMU is just a combination of inertial sensors and sometimes also, most of the time, magnetic sensors. So typically 3 accelerometers, one for each axis, same for the gyrometers, and same for the magnetometers. I would say that typically in an IMU, you do not have state estimation algorithm. There is no data fusion. You just have sensors gathered on the same board. The attitude and heading reference systems, on the contrary, are the same as the IMU, but with the addition of an embedded processor able to fuse the sensor data. And typically, it tries to estimate the best the 3 Euler angles, rotation speed. Typically, this device is not really able to estimate the positions This is more the idea of what we call an inertial navigation system. So the inertial navigation system is an AHRS with the addition of algorithms and support of aiding devices such as the GPS to be able to compute or to give an estimation of the position and also linear speeds. So depending on the type, it might not need at all time a GPS, but this depends quite a lot on the cost of the device. So for low-cost devices, typically most of the position information is computed thanks to the help of GPS or sometimes also speed sensors such as DVL for underwater robots. And the autopilot is on top of that. It's something like an INS with additional external devices support. And the main addition is the control algorithms that can be configured depending on multiple types of robots. So the problems that we have sometimes with autopilots is, and not only with autopilots, also with the other devices that I mentioned earlier, is that even though, especially for an autopilot, they try to support a lot of sensors, a lot of devices that sometimes should be able to estimate the same state variable of the robot, we still have sometimes problems, wrong state estimations, which can cause the failure of the mission of the robot or even the loss. So in this slide, I propose an example of a problem with that we got with an aerial robot. So this quadrotor was asked at the end of what it was doing to enter into the land mode, which is a typical predefined mode of an autopilot. So normally we should expect that when we enter into the land mode, the robot, the drone should land to the floor. But instead, here, what happened is, in reality, the drone started to climb quite fast up to the roof of the building where we were. So that was a quite annoying problem, and we tried to understand what happened, because on this drone we had several sensors able to measure somehow the altitude of the drone. So here on the different curves, we have, let's say, first in yellow, the values of the barometer. So we see that first it is a little bit oscillating, and then in the end, the barometer is clearly saying that we are climbing quite fast. On the robot, we had also a LiDAR, so a laser directed towards the floor. So it is the green line, the green curve. And here also we see the same types of variations as the barometer, with especially in the end, after we enter into the land mode, the laser is clearly saying that we are climbing, that the robot is going to the roof. However, the blue curve is supposed to be the final estimation of the altitude by the autopilot. So this is supposed to be the result of the internal state estimation algorithms of the autopilot, and this is probably the value used by the controller algorithms embedded in the autopilot. And we see that in the beginning, yes, it seems somehow to to be correlated to the other sensors. But in the end, when we were in the land mode, it was not really, it was as if the drone was not climbing not much. So probably that bad altitude estimation was the cause that made the drone climbing to the roof, because it was not able to realize that it was climbing. So the thing is that we see here with this example, and there are also other examples, that even though we have devices like the autopilot able to fuse the data from multiple sensors, which are able to compute the same variable sometimes, it still can have problems, even though when we think about it, we would expect that it should still be able to estimate correctly the state variables, even in the case where some sensors are failing. So in this case, in reality, probably what happens is there is another sensor in the autopilot that is probably taken into account, and probably too much, it is used with too much trust. So it probably used quite a lot the accelerometer. I guess in this case, the autopilot is mainly working on the vertical speed estimation. For that, it quite use probably a lot the vertical accelerometer, which can be easily disturbed by vibrations. And in reality, on this specific drone, we realized that there were real problems of vibrations, and this is probably that was probably the main cause of the problem. But it's a little bit a pity that we had the accelerometer maybe that were completely wrong, but we still had two other sensors, the barometer and the laser, that were correct. So something would need to be improved in this problem. So what I mean is there are still quite a lot of problems. So that's why I would like here to study more in detail some variable estimation problems, especially related to the heading and position estimation, because we often, these variables are very important for the control of the drones, and they still have often a lot of problems, estimation problems. So let's first start with a simple heading estimation problem. So first, we will assume, to simplify, that we are in just a 2-dimension, and we will imagine that we have one geometer able to get the rotation speed of the robot. So we can integrate the data on a short delay if we have a known heading value at some time. We can have also a compass, an electronic compass, which would be able to give an absolute value for the heading related to the magnetic north. But we can, to simplify, imagine that it can be easily correlated with geographic north. We could have a dual GPS, so it's a GPS with 2 antennas, which is able also to compute the heading of the robot with respect to the geographic north. And so we have these 3 types of sensors that should be able to compute the heading of some robot. So each of these sensors has its own problems. So for example, the geometer needs to be integrated, and measurement errors accumulate over time. For the magnetometers, magnetic disturbances can happen due to the components of the drone itself, or also due to some things in the surrounding environment of the robot. And for the dual GPS, sometimes it might not be available if we do not have a clear view of the sky. And also another problem is typically the GPS is not outputting data at a very high rate. Most of the time, I would say it is something like 1 data every second, which might not be enough for some control loops. So what we can realize is that at the moment, most of the inertial systems use probabilistic methods, typically that are probably designed to be very precise in optimal conditions, but we could expect that they are not much designed to detect and react in case of inconsistencies between the sensors. And on the contrary, we could expect that interval methods are quite good to detect inconsistencies, and especially in the way we design fusion algorithms with intervals, we are a little bit forced at each step to think about what could happen if we have an inconsistency that would appear as an empty interval, and probably this could help to make more reliable state estimation algorithms. So probably here in this seminar, I do not need to talk much about what is interval arithmetic. So here we will use at some point what we call tubes, intervals of trajectories, because we have variables that vary over time. So this is just an example of a contraction procedure with interval analysis that probably most of the people here know. So probably I do not need to spend much time on this. So let's talk about how we plan, well, how we can make a heading estimation with the assumption I made. So what we want is to estimate the heading psi of, for example, a boat as an interval using the dual GPS, the vertical gyrometer, which gives us a rotation speed omega, and if needed, also from the magnetometers. We will assume, to simplify, that lever arms and other problems are not considered, or considered as included in the error widths of the intervals. So thanks to the gyrometer, we can say that psi dot is equal to the measurement of the gyrometer. And what we would like to do is assuming that at some point we have an absolute value of the heading. For example, thanks to the GPS, we can integrate this equation to get an estimation of the heading at a higher output rate, or at during periods where the GPS would not be available. And we can have also some consistency checks that can be done on the GPS data to determine whether the GPS should be used or if we should fall back to the magnetometers. However, in the specific case of computations with angles, we need to be careful with the modulo 2pi problem, because probably due to equation 1, what we will get is always it could be an always increasing psi value, while the sensors are probably giving angles in an interval between -pi and +pi. So we need to be careful with that. So what we propose is, instead of working directly with operations on angles, we can instead manipulate the cos and sin of the angles, and to be robust with respect to the modulo 2pi problem. So we can rewrite the problem with a state vector with cos and sin, and rewrite the equation 1, and find a way to integrate that equation. So one first way to quickly integrate this equation is we could integrate it with Euler method, for example, or other integration methods. But in this specific case, we can have an exact solution, so that if we have some value at a specific time of the heading, we will be able to compute an estimate of the value at next time step, taking into account the geometer values. So in addition to that, we can also take into account some consistency equation, which is related to trigonometry due to what we have chosen as state variables. And I would say the last difficulty is, since to overcome the problem of modulo 2pi, we are now working with cos and sin. At some point, we need to go back to get the angle from the cos and sin. So for that, an existing contractor in interval arithmetic already exists, and it is called the polar contractor. So it's okay to go from cos and sin to the angle itself. And the idea is that with all these interval computations, if at some point we have an empty set, we need to think about what to do. So there are probably several strategies that can be done to react in case of we have an inconsistency, for example, between the heading given by the GPS and the heading that we get from the geometers. So in the end, the problem can be written as this, which is quite typical with these variables, as I said before. So we assume that we have geometer data at all time. However, GPS is only available at some time instance. And for the magnetometers, if needed, we can have also data almost at all time instance. So to validate this idea, we made some comparisons with existing inertial navigation systems. So the system that we tested is first our own system with the algorithm I described just before. So our system was physically based on the sensors from this type of AH or S, so especially the geometers. And we had dual GPS separated to that. And we used also, when needed, the magnetometers inside the SBG AHRS. And for the interval estimation algorithms, we used the codec library on an embedded computer. So this is our own system. And the other systems, to validate the first one, were Pixoc for Autopilot, also with a dual GPS, and another type of SBG INS with its own dual GPS and its own algorithms. The experiment we made was with each of the three systems. First, we put the system at an angle towards the south. Then we turn it towards west and go back to the south. So this is just to check that normally we are in nominal conditions and the value should be correct for all of the systems. However, after we try to generate inconsistencies to be in non-nominal situation. So what we do is to generate the inconsistency, we leave the GPS antennas where they are, so towards the south, but we turn the geometer part of the system. So there should be an inconsistency. We have the GPS antennas that are still towards the south, while the geometer is turned towards the west. So and then we go back to the initial position and see if the system is able to recover after some time from this inconsistency. And the other thing that I forgot to mention is while we generate an inconsistency between the angle of the geometers and the GPS antennas, we also try to move rapidly the geometers so that they saturate. So there are two types of problems that we introduce in this experiment. So this is a picture of our own system. So you have the two GPS antennas, and our geometers were inside this, and the embedded computer was somewhere in this box. You see in the middle another type of expensive inertial navigation system. So I do not talk about what we did with this system. It was just considered as a ground truth to have an idea about the accuracy of our own system. But the experiment I just mentioned before is more about the detection and the robustness in case of inconsistencies. So first, here you have the data of the ellipse D commercial system. So on the top, you have in light gray the evolution of the heading given by the GPS, and in black the evolution of the heading returned as a final state estimation of the system. So in the beginning, we are towards the south, so the GPS and the final heading estimation are the same. Then we turn towards the east, so here also we are in nominal situation, so everything is okay. Then we go back to the south, up to the point where we try to generate the inconsistency by moving a lot the geometer part, while we do not move the GPS part. So that's why the GPS data are still towards the south. So this is normal. But on the curve below, which represents in gray the geometer data, we see that we are shaking the geometers quite a lot here and probably making them saturate. If we check the limits of the geometers, we can check that we indeed reached the saturation of the geometers. And what we see is after this generated inconsistency, the system is unfortunately not able to give us the correct heading. So it is giving some. So probably what happened is the system detected some inconsistency between the the GPS data and geometer data, but it seems that it chose to ignore the GPS and rely probably on the geometers, while the problem is that we tried to saturate the geometers, so it was probably completely wrong. And this is what we get. And then when we move back the geometer part to the initial position, it sees the movement, and we see that there is probably a difference of 90 degrees, which corresponds to what we did. We moved from the west to back to the south, but it's still not the correct value, because we should be towards the south as the GPS is saying. So we have a big problem here. Then the same experiment for the Pixoc autopilot. So we can see here that the behavior is different, but maybe in some way better, but not probably not perfect. So we see that after the inconsistency, the heading estimation is bad, but so it is slowly converging towards probably the GPS value, up to the point when we move back the geometers towards the south. So it probably sees the geometer rotation, and then slowly converge again towards the GPS value. So this probably is a kind of characteristic of some kind of weighted average between the data given by the geometers and the data given by the GPS. So this is the behavior for the Pixoc autopilot. And then this is the behavior with our own system based on the interval fusion algorithm. So we see that during the perturbation, so during the moment where we are shaking the geometers, everything is bad, but quite immediately the final estimation goes back to the correct value, which corresponds to the GPS heading. And after, we made also other movements to check that everything is still okay. So so it seems that in this, at least in this case, we can say that our method is competitive in the way that we are able to handle better this type of inconsistency compared to other existing systems. So after we made some tests on a real boat to validate that on a full robot, we can have the full control loop using our state estimation working in real conditions. So I can show you a quick video of the dynamics of the robot. So in this video, the robot was not making an autonomous trajectory, but it's just to see the dynamics of the robot. So it is a robot based on a water jet motor that can be oriented. Okay. So the experiment we made with an autonomous control algorithm is this one. So a typical survey trajectory in an area, and we can see so the waypoints in yellow that are linked in red, which would be the ideal trajectory, and in green we have the GPS position of the robot. So what we want to say here is just we can validate that we can validate that our heading estimation algorithm is accurate enough to be used in an autonomous robot for survey missions. But probably it has to be said that we we are not claiming that we are more accurate than the other systems. We are just accurate enough for this type of missions. And also, some point that I forgot to mention is when we made the comparison with the other systems, we used the default settings of the different devices. It's still possible that with other settings than the default ones, potentially the other systems could behave better than what I presented before, but this would remain to be checked. So this part was about heading estimation, but now I would like to talk a little bit about position estimation. So I just want to mention that with interval methods, we can make a position estimation of the robot, in addition to the heading estimation I previously mentioned, and with different types of models for the problem. So here I propose a simple, I would say, a simple model for the dynamics of our boat, which is something somewhere in between the very simple model of the Dobbins car, but which would be maybe a little bit too different, a little bit not accurate enough for our specific boat. And still, we did not want to go into a very complicated model for the robot, so we made some kind of compromise. So just to give an idea about what gives this model if we test it in simulation, I can show you. So we'll. So this is a simulation with the key of the keyboard of the dynamics of the model I presented. So we can see the behavior of the dynamics, and this probably is quite similar to the dynamics that we have seen on the video that I just shown earlier. So if we try to estimate the position of the robot on an experiment similar to the one we made with a real robot, we can get this with the assumption that we had the GPS position in the beginning of the experiment. So the beginning was here, and at some point we lose the GPS. So that's why in the end of the experiment, it seems that the uncertainty, the position uncertainty is bigger. So for that, we use this equation integrated and with a similar algorithm as the one that I described for the heading estimation with intervals. And then we can consider another scenario of position estimation, where in this case, we will assume that we have on the boat a DVL sensor. So this sensor is able to provide the speed vector in the robot's coordinate system. So if we want to take into account this sensor, the model to be used in the state estimation can be this one with or just the rotation matrix given especially in 2 dimensions by the heading estimation. And if we make another experiment with the real robot and assume that in the beginning we have the GPS, but after some time we lose the GPS, using the model I just described in the previous slide, we can still be able to compute an estimation of the robot position using an interval algorithm. So to sum up, what we consider is that with that first test, we were able to make some heading estimation from a fusion of multiple sensors, and that this estimation is able in some situations to be more reliable in terms of inconsistencies. And this system is able to be used in a real robot in typical survey missions. However, there are a lot of improvements that would remain to be done. So probably one of the obvious first one is to go in 3D and especially take into account the roll, pitch, and altitude estimation. There are also many improvements that could be done in the interval fusion algorithm proposed. For example, using the idea of fuzzy outliers that were studied in previous works, and also multiple types of disturbances should be taken into account, especially the case of misleading GPS data. So I would say that's all for now, and I'm ready to answer your questions or remarks.
Okay, then many thanks, Fabrice, for your interesting presentation. And yes, I'll just pass the questions that you just asked at the end to the audience. Is there anyone who wants to start with asking anything to Fabrice? Yeah, Carlos.
Hi, do you hear me well?
Yes.
Perfect. First, thank you for really nice talk. I always like to see this kind of application because it's a real application, and that's something that unfortunately I haven't had the opportunity. But I have some kind of questions, and it's regarding the real application, because since my point of view, I think that this is a problem of fault detection, because when one sensor is not reliable, so if you are able to detect a fault, you can report the faults and just try to ignore it, or based on something similar, right? So my first question should be, in a real application, I would solve this problem with redundancy of the sensors. I mean, I would have 2 or 3 sensors. However, depending on the real application, you cannot have more than something. So based on a real application, on your application, how many sensors can you have for each variable? And apart from that, you are detecting the faults. So when you are detecting the faults, I'm assuming that you're going to have some empty intersections when you are going to make the data fusion. So you are reporting this like a fault, and and how do you weight which direction are you going?
Okay, so I would like to go back to okay, so in the specific problem of heading estimation, what we considered is that we had here 3 sensors that helps for the heading estimation. So the first one is the geometer that needs a model, so to integrate. Then we have the dual GPS antenna, which is able to give an absolute heading information, and also the magnetometers. So in this case, we have 3 sensors. Some of them are quite typical, especially nowadays. The price of this sensor is lower than maybe previously. And on probably each sensor, we can think about consistency or reliability equations. So, for example, for the specific case of the dual GPS, there is something that can be used to have an idea whether the data are correct. So the thing is, you have 2 GPS antennas, and at some point, typically the user needs to measure manually what is the distance between the 2 antennas and provide it to the inertial navigation system. And then during all time, the inertial navigation system is also trying to compute by itself the distance between these antennas. So there are at least two things that we can take into consideration in this specific case. First, there is a value provided by the user in the beginning. So if at some point during the experiment, the GPS does not measure the same value, that means that probably the GPS should not be taken into account. And even if the user did not provide a value for the distance of these two antennas, what can be considered by the system is that the distance between the two antennas should be a constant. So if the system sees that the distance is varying too much, that means also that there is a problem. So that could be an example of something to weight, to have a weight about the trust that we should have on this sensor. And this goes back to the prospects that I mentioned. Indeed, to what could help to make the fusion between the data from different sensors is so first, what is probably quite well known by some people is using the relaxed intersection. So in the case of the relaxed intersection, we assume that in normal operation we could have, let's say, one sensor among three that can be wrong, but this is probably not accurate enough. So what was proposed in the paper that I mentioned here is a fuzzy interval intersection, which typically, instead of having a weight of 1 for each sensor, can provide other things to make the fusion.
Okay, but now I got the whole idea completely. But regarding the problem itself, I mean, imagine that I have this chip, and you gave me the problem that I have a problem with reliability. I just gonna add 2 more antennas in another places, and I'm gonna add another magnetometer, that sensor, and another gyroscope. On that way, I'm gonna have different. I'm gonna have the redundancy, and I can check if it's good or not. I mean, I can solve this problem without the need to use a robust estimation. Of course, okay. I mean, it's more about exactly when do you need it, why. It's okay. More.
So what I try to mean is that in the beginning, for example, with the experiment with the drone, so we have an autopilot which is probably using some kind of Kalman filter or probabilistic method to fuse the sensor, and we had the laser giving the altitude, we had the barometer giving the altitude, we had the accelerometers given the altitude, and still I don't know what they did in their algorithm, but it doesn't work. So what I mean is that there is something to be done in terms of algorithms without adding additional sensors. At the moment is wrong.
Okay, that's fair enough, definitely. Thank you. Yeah.
Okay, do we have further questions? Because in fact, the discussion between Carlos and Fabrice already has stolen one of the questions concerning the relaxed intersection that I wanted to ask. But I would like to ask some further aspect, because you're still doing something like a data fusion using an interval method between different types of sensors. And the important thing is that the different sensors, for example, gyrometers and GPS, that they are temporarily synchronized. And especially when you're dealing with low-cost sensors, I think this is mostly not the case. How do you deal with this aspect of inconsistency?
So at the moment, I would say probably we do not deal with it the best way. Most of the time, the first approach is we assume that this error is included in the errors that we put for each measurement. But I remember that for the heading estimation part, something was done to try to have a better idea on what are the respective delays between the measurements of the different sensors. But I would say at the moment it's not probably correctly formalized, at least in what we did. And for sure, that would be some work that would remain to be done.
It's because I think in cases where you have some sensors for which you have to integrate the signals temporarily, I think it's quite easy. Then you have an uncertain time span of integration, and then you could include the corresponding values just in the corresponding interval as the outcome. But if you're directly using the sensor information without any additional signal processing afterwards, and you just have at some point in time where you don't know where it is, the measurement, I think that's more tricky. And I think you still need some assumptions concerning, for example, the variations of your state variables, that you assume, for example, that they are smooth or that they do not change, is, let's say, the sign of the first order derivatives or things like this, that you can find some kind of inclusions over the measured quantities over two subsequent time steps. Maybe this could be some trick, but I think it's definitely an interesting question to investigate further. Yeah, at the moment I do not see any further question, therefore I just continue. I have a further, let's say, remark or question concerning an extra functional property. When you're comparing your different algorithms, for example, using, let's say, an unscented Kalman filter, you just have pointwise evaluation of your system models. In the case that you're performing interval computations, you need to compute with sets. And the set computation typically is more demanding concerning the number of arithmetic operations that you have to perform, that you get definite enclosures. Did you make some investigations concerning the energy consumption that your algorithm requires with respect to, let's say, some state-of-the-art methods?
So I would say the short answer is no, but I would say I do not expect that it would be much a problem, but no, I cannot guarantee that it would be worse or better.
It's because, for example, when I assume you're doing multiplications of variables, of interval variables, in many cases you really have to evaluate all possible combinations of lower and upper bounds to be multiplied. And in such a way, you immediately have 4 multiplications instead of a single one. And this could turn, I think, especially from a computational point of view, the algorithms are more demanding, but I think it would be interesting also to see whether this has an effect or not on the autonomy of the system.
Yes, it would remain to be done, yes.
Okay. Do we have any further questions from the audience? Okay. This doesn't seem to be the case. Then, yes, many thanks again, Fabrice, for giving this presentation, for being the first speaker in our seminar series after Christmas. And yes, I really very much enjoyed your presentation today. And I'm also looking forward to our next seminar that we will right away have Friday next week. Our speaker will be Robert Dehnert from the University of Wuppertal. And yes, he'll present his work on combining set-based and also stochastic techniques for control design and state estimation. And now the only thing that remains for today is to wish all of you a nice Friday afternoon, weekend, and see you soon next week. Yes, in our seminar.
Thank you. See you.